We found a Laplace transform rule that turns multiplication in the t world by an exponential into a shift in the s world. That kind of makes you wonder, is there a corresponding rule that would would somehow involve shifting to the right in the t world? Maybe by symmetry you might think you would get multiplication by an exponential in the s world, but there's an issue that we have to deal with, which is what about the past in the t world? So if we have two functions, say one that looks like sine and another, these are both in the t world, and another function that is 0 up until t equals 0, and then it looks like sine. The Laplace transform is going to send both of these to the same Laplace transform. It's going to send both of these to 1 over s squared plus 1. And the reason for that is because the Laplace transform is an integral built out of an integral from 0 to infinity on the t-axis. And so the Laplace transform actually doesn't know anything about what happened in the past. So the Laplace transform treats these two functions as the same. But when you shift them to the right, all of a sudden these two functions won't look the same, because the one on the left, if you shift it to the right, you pick up some of the additional oscillations of sine. But the red one here on the right, if you shift it to the right, you're shifting some of this place where it's 0 over to the right. So we can't really expect there to be a nice rule for the Laplace transform of just a shifted function like this, because what you get for the Laplace transform actually depends on what happens in the past of the function f. So this just isn't going to happen. What we need is some way to chop off the past of the function if we're going to shift it. And the way to do that is with a function called the Heaviside step function. It's usually denoted t, often with a script u. I'm not sure why u, but that's the traditional letter for it. The function u of t just chops off the past, essentially. So it's 0 if t is less than 0, and it's 1 if t is greater than or equal to 0. So this function is 0, and then at t equals 0, it jumps up to 1. Now, the reason that I say this chops off the past is because if we say take this step function and multiply it by sine of t, let's graph the result. Well, for negative t values, the step function part is going to be 0. So the sine part doesn't survive. It just gets zeroed out since it's being multiplied by 0. But then at t equals 0, the step function all of a sudden turns into 1. And so for positive t values, it looks like 1 times sine of t. And that's just sine of t. So the effect of multiplying by the step function is to cut off the past, zero out whatever happens in the past. So then if you wanted to shift, if we want to shift sine to the right, we should really multiply it by the step function first. So if we're going to do a shift in the t world, we have to multiply by a step function just to have some hope of the Laplace transform acting in a way that is at all predictable. So when we go to calculate the Laplace transform, we'll expect there to be a step function here. Now, one nice effect of having this step function at our disposal is that it lets us turn functions on and off. You can see the effect of multiplying by the step function is it turns off sine of t for negative t values, but then turns it on at t equals 0. So we can use the step function to turn functions on and off, and that lets us write piecewise functions in a nice way. So let's look at a couple examples of doing that. So let's express this function, this piecewise function, using our Heaviside step function. So this is 0 for negative t values. And then at t equals 0, it turns on and becomes natural log of t minus 5. So to turn on at t equals 0, that's what the step function does. And then we're going to multiply this by the function that we want to turn on. And the function we want to turn on is natural log of t minus 5. Okay, so I guess this wasn't a great choice because t minus 5 isn't even defined for some positive t values, so why don't we make this t plus 5? There, that works better. Okay, now let's look at this example. So for this piecewise function, it starts out for all t values below 1. It's just t, so we'll start with t. Now, at t equals 1, we need to turn this off. So we need to have some influence that starts at t equals 1. And so we need a step function that turns on at t equals 1. And the step function that turns on at t equals 1, well, that's the regular step function, but it's shifted to the right one. So this step function turns on at t equals 1. So what we need to make happen at t equals 1 is we need to cancel off this t. So we need to subtract t, but we need this subtraction to happen at t equals 1. So far we have a function that starts out acting like t, but then at t equals 1, it becomes 0. So now we just need to add on what we need to have happen at t equals 1. So we need to add e to the t, but we need this e to the t to become active at t equals 1, so multiply it by a step function shifted to the right one. Of course, you probably want to factor out the u of t minus 1, so this is u of t plus u of t minus 1 times the function we're turning on minus the function we're turning off. So you can see that by some combination of step functions, you can write any piecewise function using these step functions. Of course, the more cases you have in your step function, the more terms you're going to have with different step functions all shifted for different values. But it's good to know that no matter what the piecewise function is, we can write it in terms of Heaviside step functions.